Hello, my name is Haadi and I was a Pawsey summer intern for the years 2022 to 2023. A little bit about me is I have recently completed my bachelor's degree with honors in physics and I have a strong passion for physics in general and also computer science. My project with Pawsey over the summer was on the modeling of electron collisions with ions of tin. The first question that comes to mind is, why tin? Well, tin is currently a very important material in the field of plasma physics. The primary examples of the use of tin-based plasma come from the fields of fusion power generation and also extreme ultraviolet lithography. First, we will discuss its uses in fusion. Tokamak fusion reactors such as ITER suffer from erosion of their wall tiles due to bombardment from the hot fusion plasma they contain. This erosion is a big problem as it leads to increased maintenance costs and also introduces unwanted species of atoms and molecules into the plasma. This damage is primarily a problem for the diverter region of tokamak fusion reactors. The diverter has the primary role of removing unwanted species from the plasma and also extracting heat. As such, it experiences a greater amount of damage compared to other regions in the reactor. In ITER, this component is made using a tungsten monoblock design, which is expensive to replace. To deal with this, a liquid metal design for the diverter is being developed in which a tin liquid metal layer will protect the solid diverter components. The accurate modeling of fusion plasma is required to fully understand the implications of the addition of tin in the diverter region. Microchip manufacturing includes a process called lithography, which is when light is used to imprint circuitry on silicon wafers. An advanced technique for this process is called extreme ultraviolet lithography, or EUV for short. The light needed for the EUV process is generated using a hot and dense plasma produced by the vaporization of molten tin droplets. The exact source of the light from within the tin plasma is still not well understood, and further studies are required to model this plasma and gain insight. For both fusion and nanolithography, the accurate modeling of plasma involving tin is required. To this end, reliable and comprehensive collision data for electron collisions with tin and its ions is required, which is what we are producing as part of this project. Now we will discuss some of the basic ideas of quantum collision theory. When an electron collides with the target atom or ion in its ground state, there are three main outcomes that can occur. These include elastic scattering, excitation, and ionization. Elastic scattering is when there is no energy exchange between the projectile electron and the target. Excitation is when the projectile electron deposits some of its kinetic energy to the target and excites it into a higher energy level. Finally, ionization is when the projectile electron deposits enough energy to strip away one of the electrons from the target atom or ion. We want to study these processes for electron collisions with tin 2+. We want to calculate something called the integrated cross-section, which is analogous to the probability of transitioning from an initial state to a particular final state of the collision system. For our calculations, we use a fully quantum mechanical approach called the relativistic convergent close coupling method, or RCCC for short. This is a powerful theoretical method that models electron collisions with heavy atoms and ions, such as tin 2+, and produces the integrated cross-sections we require. The first step of this method is to model the energy level spectrum of tin 2+. There are two components to this spectrum, the bound levels and the continuum states. In real life, there's an infinite number of these states. The RCCC method models these states using a finite number of pseudostates as shown in the diagram. As the number of these pseudostates is increased, the calculations become more and more convergent to reality. However, this also makes the computational resources required increasingly large. The second step is to perform the electron collision calculations and produce the desired cross-sections. This is done by solving the Lippmann-Schwinger equation as shown on screen. The T matrix, as indicated on screen, is the solution we require as it contains the information we require to compute the integrated cross-section. But before this can happen, the V matrix must be calculated, which can be a very computationally intensive task based on the number of pseudostates included and can require hundreds of gigabytes of RAM. The RCCC method is implemented in Fortran using a hybrid OpenMP-MPI approach for parallel computation. This allows the calculation to be spread over multiple nodes and use all the CPU cores available on supercomputers such as Photonics. We were successfully able to calculate cross-sections for all the processes we were interested in during the time of the internship. Here are some of the integrated cross-sections we obtained for electron collisions with tin 2+. The first figure on screen shows the ionization cross-section as a function of projectile electron energy for many scattering models. The The convergence of this cross-section can be seen in this figure, as the increasingly large models produce cross-sections that are closer and closer together. The figures on screen now show some of the excitation cross-sections we produce for transitions to low-lying states in the tin2+ bound spectrum. Cross-sections such as these ones are very important for plasma modeling applications, and this is the first time such data has been produced for tin2+. Overall, I really enjoyed working on this project with Pawsey and with my supervisors from Curtin University. I learned a lot about the physics surrounding my project, as well as using supercomputers for scientific research. Learning about and working on my science communication was also one of the key outcomes I obtained from this internship. These valuable skills are something I will take forward into my future career. Thank you for watching.